The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, shall we start? As always, just open for questions about any topic. I listed again trusses, 1D finite elements, grad div curl, and I should have squeezed in x plus iy too as the magic trick for finding solutions to Laplace's equation in 2D. So those are all certainly topics that are in this part of the course. We didn't really get to 3D. I'm sorry about that. Where the curl comes in, maybe I can say a few words about curl today. Anyway, questions, discussion. Yes, thanks.
Is there any way to construct ATA for a truss without knowing all of A?
Let's see. So ATA for a truss, that's a good question. So trusses, ATA. I guess I don't know any magic tricks either. So one way is to construct A or A transpose and then just multiply. The second way to do it would be by the 4x4 bar element matrices so go bar by bar. So 4x4 bar matrices, 4x4. So those are already in the A transpose A form. They're A, like little A element, A bar transpose A. Gee, this isn't as great as it should be. A element. So those are, but I don't know that would be. So and then you pop those into their correct places. I don't think I know any great idea beyond that. So I think you should really be ready to construct a matrix A. Yeah. For a reasonably small truss, of course. Yeah. And of course, the other part of trusses, the fun part is to be able to recognize solutions to AU equals 0, possibly by looking at the truss more than by solving AU equals 0. Yeah, any particular example of a truss that I should look at just to pin this down? Any favorite trusses? There was an exam question. What was it? A complicated truss? Or let's just create a truss and just think about it. Maybe I won't create the whole matrix A. Here's a truss. How's that for a truss? So it's got and let me put no supports on it. Just there's a truss to think about. Probably we won't get to all the gory details, but if you look at that truss, what's the shape of A? Shape of A, of the matrix A. I have a row for every bar, so 1, 2, 3, 4, 5. And how many columns have I got? How many unknown displacements have I got? 8. 2, 4, 6, 8. So I would expect AU equals 0 would probably have how many independent solutions? 3. You don't know the exact rank. That's exactly true. It could be there could be more than 3, right? So to really pin it down, you'd have to be sure you were right about that. So 3 at least. And I guess here you could tell me the three solutions to AU equals 0? 3 rigid motions. I could translate it to the right, I could translate it up, and you would know what the U is, so U translating to the right would be 1, 0, 1, 0, 1, 0, 1, 0, right? That's horizontal motion, all the same, rigid motion, and we should certainly discover that if we created A for this truss, that AU was 0. And similarly, vertical motion, and the third one would be rotation, yeah, a rotation. So if I did the rotation around there, for example, this U would also be this would be a 1, 0 here. This wouldn't move. So this, I'm putting in the 4 pieces that would go into U. This one, what would be the U for this, the displacement of that corner of the truss in a rotation? So my rotation is just swing this whole thing around. 0, 0, -1, I think, right? Because it's not going to go out, it's going to go straight down, 0, -1. And what do you think this guy is? 1, -1, let's see, it's going to go this way, so it's going to go forward and down, and I think you're right, 1 and -1. Yeah, I think that would be right. Yeah, then the truss, we could check each bar should, that bar, for example, should not change length because the movement is perpendicular to the bar, and I'm writing 1s, but I really should write some much smaller number, like 0.1 everywhere or something, just so that this isn't a very big angle and it wouldn't change length to first order. Yeah. So that's maybe an example where we see the motions, but we didn't actually create A, and we should be able to create A. Don't let me prevent you from thinking about A. Yeah?
The coefficients of the upper right node, should those be 1s or should they be like √2/2?
Well, that's a good question, and after many years, I've figured out that they're 1s. But it's a very good question. Let's just see why. This guy is, let's look at this bar to be sure it's not stretched, right? So this guy is moving over by 1, and this also by 1 is my claim. And then this movement down doesn't stretch it to first order. Yeah. So I needed to make those guys the same. Yeah, I guess what I figured out is that if you're rotating around here, then it's somehow it's the X and Y. Is that, anyway, whatever. Maybe, yeah, that's it. So that gives us a chance to do a specific example. Yeah, right. Good. Okay, but I've dodged the creation of A. Just, yeah, thanks.
How to see the distribution of forces in the truss, like the solution to A transpose W?
So the solution to A transpose A.
So the forces, because here we are looking at movements, but what about the forces?
Yeah, I see. Okay. So the reason I stopped here was that A transpose A will be singular. So I wouldn't go forward to A transpose A U equal F, but if I put on some supports, then of course now all good. So now I have how many? What's now the shape of A for this one? I now have, this bar is now, forget it, right? This bar is just between 2 supports. So if we put it in the matrix, it'll just be a row of zeros. Nothing will happen, and we're better off to just knock it out. So I think now I now have 4 bars, and how many unknowns? 4, 2 there and 2 there. And do you guess that it's stable, that truss? Yeah, that looks stable to me. So the 4x4 matrix would be invertible, and then I could solve. your good point. Then A would be 4 by 4, A transpose would be 4 by 4, C would be 4 by 4 in between. This is the case that I gave the name for this case. When I have a square matrix, do you remember the name just for the hell of it? Statically determinate. It's determinate because each step determines everything completely. Normally, if I have another bar there, now it would be 5 by 4, and now I really have to do the A transpose CA to get to a 4 by 4 invertible. By itself, A would not be invertible. This is the more typical case where you really have to put all three together. Right. Yeah. I hope you enjoyed the trusses part, and continue to enjoy them this evening, right? And then forget, right? Okay, I'll just keep moving to be sure that we cover any other topics. Yeah, thanks.
Could you write down what A would actually be?
For this matrix? For that truss? Oh my God. Okay. Let me see. Then can I do one row? Okay. Of course, you guys are responsible for much more. But all right, which row shall I do? Which bar? A diagonal bar? I knew you'd make it. Like you could make up quizzes, and I could just sit back here. Okay, so let's take this diagonal bar. All right. And are we going to keep that supported or not? Do you want to keep it supported? Okay, so in this case, then that end is not moving. So this will be in this bar corresponds to a row of A. And how many non-zeros will I expect in that row? Just 2. Normally 4, but I'm not getting any motion down here. So it'll just be 2. And if that's 45 degrees, shall we say, then that row, I think, would be what? Well, okay. Where do my non-zeros appear? This is node number 1 with an H and a V. So I think we have zeros. If that bar stretches, you know, the connection between displacement and stretching of this bar does not involve this guy. So I think it's 0 and 0 there. And now, what else is it? So now come the real numbers, which I believe to be cosine and sine of that angle. Because if I, right, how much does that bar stretch? Yeah, if I know that I'm looking for a cosine and a sine, and if this goes positively, then the bar does stretch. If this goes positively, that does stretch the bar, so I'm expecting positive numbers there, like the cosine square root of 2 over 2 and the sine square root of 2 over 2. Well, I dodged the bullet of getting the whole matrix, but maybe that would do it. Why don't we do this top one? Yeah. Tell me the top, the first, if that's bar 1, what would be the first row of the matrix? Okay, it involves both of these nodes, but the angle is 0, so that's going to be a little special. So what would this bar, if this goes out horizontally, that's, oh, yeah, I should really start with the first one. If this goes horizontally, it compresses the bar. I think we get a -1 there. If it goes vertically, that doesn't do anything. If this goes horizontally, it does do something. If it goes vertically, it doesn't. I'd say that would be the row of the matrix coming from the top. That would give me the stretching. You remember, I'm always going to, I think of multiplying this by U. I think of multiplying that by U1H, U1V, U2H, U2V. And this top row should give me U2H minus U1H, which is this is the stretch in bar 1. Yeah, yeah, yeah. So that would be a typical one. This would be at least typical of one where I do see a cosine and a sine. And if, let me just finally add, suppose this was not supported. Okay, suppose that's not supported. Now I've got a couple more columns to squeeze in. Maybe I can somehow do it here. Can I squeeze in the 2 more columns? So what, can you complete the top row of the matrix? Now I've got 6 columns, because here's 2, here's 2, here's 2 more. What goes in the top row of the matrix now? Zeros, because this is not affected by bar 1. But it is affected by this bar. So it's going to show up in this row, and how will it show up? 2 negatives, right. A negative cosine and a negative sine. And at 45 degrees, I can't tell the difference. Yeah, because if these move forward, that compresses the bar, so the minus sign. So again, the rows add up to 0, as we expect when the bar is not touching a support. This is not touching a support, so so it adds up to 0. Yeah. Okay, that's, yeah. We'll have a truss problem this evening, but not a big messy one. How about finite elements? You guys, do you like finite elements? I'm sort of hoping to make them attractive. I noticed a problem, just to give us some specific one to work on. I don't remember that it was a homework problem. This is section 3.1, number 18, asks about the equation u double prime equals 0. Well, we've talked about it in class. With u of 0 equals 0, but u prime of the slope equals 0 at the other end. So what's the picture if I use linear elements? I don't remember how many used in the problem. Well, it allows you to use n interior guys, 1, 2, up to n, and then another, this will come in, or that's the point. Okay, so what's the finite element method? Finite element matrix K for this. So I want to do linear elements, and I want to construct K. And yeah, I guess, oh, yeah, I haven't actually made anything happen to this problem. All zeros is kind of slow going. U will be, the solution will certainly be 0. So maybe I better put in a load here to get some action. Okay. Well, yeah. So I propose this question, but now is this a question to think about? I think that's a reasonable example to do. It's got the 2 types of boundary conditions. It's got the right-hand side F. It's got linear elements, which means it's kind of doable by hand, and we kind of know what matrix to expect out of it. What matrix do we expect? What do I expect out of linear elements? You remember the point about linear elements on equally spaced meshes? That just brought back our regular difference matrices. So I'm expecting the stiffness matrix to be a difference matrix. Anyway, the point of this question is, okay, I have a hat function, I have a hat function, I have a hat function, a hat function, and is that the end? Is that the complete list of my trial functions? One more, right? Because this condition is, all my trial and test functions don't have to satisfy this. So I'm allowed and should have another guy there, a half hat for for that one. That you may say, don't let that clown into the finite element space, but I think it should be. The solution won't use much of it because the solution is going to aim for zero slope. But it's going to need a little bit. You see why it needs a little bit something here? Because this thing has slope down. So if there's some of that in there, there better be somebody else to cancel it if our approximation is going to have about zero slope. Okay, so then can you construct the matrix K? Let's see. What's the 2, 3 entry? So if I call this number 1, this number, oh, I've already numbered. So number 2, number 3. So that trial function against that one. What's my formula for the 2, 3 entry of the stiffness matrix? It's some integral, right? And what do I integrate? I integrate, yeah, now we've got to have to remember. So I do, yeah, my weak form, I've integrated by parts, so my weak form is the integral of u prime v prime dx equals the integral of f times v dx. That's my weak form. I did 2 integrations by parts, and the integrated term will go away because of those zeros. Okay, so K23 will come from this side when I'm using phi2 and phi3, because I'm taking the phis and the v's both the same hat function. So phi, okay. So what do I get for that? Phi2 prime is, so where is this? This is it, and it overlaps this one. So when it overlaps, this phi2 is coming down and phi3 is going up, and the slope is 1 over n plus 1 over h, let's say. So I think I'm integrating a negative slope. Is that right? Times a positive slope, and I'm really only integrating it over one h interval. The two overlap only here, where this one's coming down and that one's going up. So I think dx, and the great thing is, of course, we have a constant, so I have minus 1 over h squared times h. I think minus 1 over h. That would be K23. Yeah, that's a simple example, and then at the end we will see it. We'll see this one. I think we'll get some matrix. We'll have this 1 over h outside. I think we'll have something like 2 minus 1, 2 minus 1 minus 1, and then only a 1 from the half hat. I think that's, so it would be that matrix that would be K. I think maybe with greater size if we have a whole bunch of elements, but that pattern. Are you're pretty much into this? Yeah, I mean, we're doing a lot in this course. You know, I'm really grateful you guys stay with it and capture these new ideas through doing exercises and so on, because there's a lot here. Well, I thought I'd put an example up to open up, just to remind you what that language is about there, and to be ready for any question in that topic, or any question whatever. So I jumped in with finite elements, but I'm ready to also to talk about that area of the course. Yeah.
When you're looking at the
X plus iy stuff, okay.
any function of
Basically any function of x plus iy, yeah. Any function. So strictly, yeah, I mean, a mathematician would say, what? Any function? That's, you've opened the door to crazy things saying that. So what I really mean is we have these powers of x plus iy, and then we have combinations of them. So the only requirement would be that if I want to take an infinite combination, the series should add up to something.
So if it has a nice Taylor series.
If it has a nice Taylor series, then that's what the world is. Those are the best functions there are.
Okay.
Functions with nice Taylor series. I'll just say it, having used those words. Suppose I take that function. There's a function, that's a function, z is x plus iy. But z is shorter to write. So it's not a polynomial, obviously, but it is a function of x plus iy. Well, tell me this. Where does that function go wrong? So e to the z is a function that never goes wrong, right? E to the z, that series always converges. What's the series? Oh, yeah. Can you tell me the series that, if I expand that in a series, what series am I looking at? Are you guys, this is not on the exam, so to speak. But it's, do you know 1 over 1 plus something? What's the series for that? Well, the constant term, when z is 0, is certainly a 1. I think the trick, it's just this geometric series, and because it's a z squared, it's that. That would be the geometric series with constant ratio z squared. If I multiply that by that, 1 plus z squared times that, everything will cancel and I'll get the 1. That's it. So there is a Taylor series for this function. Now, the reason I chose that example is you could tell me it doesn't converge if z is too large, right? Is this an analytic function? Where is this a good function, and where does it have problems? If z is less than 1, and I really mean magnitude of z, so here, let me draw the z plane. Here's the real part of z that you usually call x, and the imaginary part of z that you usually call y, because z is x plus iy. And where will this series converge? It'll converge out as far as this circle. It started at, this is the Taylor series around 0, right? The constant term I found at z equals 0. Then that series, this function is great. It's an analytic function. Everything, it gives us a solution to Laplace's. This will be, the real and imaginary parts of that will be the u and the s that solve Laplace's equation. Out to, at least in this circle. But something, there's a problem at the edge of the circle. Now, here's my point. If I think of 1 over 1 plus x squared, look at that for a minute. That function has no problems at all, right? 1 over 1 plus x squared, you can let x be anything. It's no trouble. But 1 over 1 plus z squared, when we look in the complex plane, we find a problem. And where is a problem with this function? At z equal, so everybody looking at this guy, there's a problem with that function at z equal I. And it happens to be, no, not an accident, it's right there on the circle. It's hiding in the complex, it's not on the real axis. So the real person didn't notice it. But the complex person said, that's the problem. There's a singularity there. And of course, it's called a pole, and people in so many parts of science are interested in that. Is there any other place that there's a problem? At minus I. When z is minus I, we'll also get a problem. So this is a function with 2 poles those two poles, and they're the reason that the series couldn't make it. If going out this way, the series doesn't meet any problems. But the series always goes out in a circle, and the first circle, the first problem it hits, the series stops converging. Yeah. By the way, let me ask you a question. Suppose I instead did the Taylor series around this point. Now, what do you mean? What do I mean by that's the point 1, let's say. What do I mean by that, the Taylor series around 1? I'll rewrite the function as 1 plus, oh no, what do I do? I want it in z minus 1 squareds. Oh gosh, I'm getting beyond what you care about. Again, if I wrote a power series in powers of z minus 1, what circle would it work in? And then I'll stop with this example. The circle would reach out until it hit a pole, and it can't make it past that pole. So it would be a circle of radius square root of 2. There would be a circle there. If we were going to discuss, and this is really chapter 5 of the book. I mention it because you've got a book that explains this. If I thought the center of the universe was there and then the poles are still here, the circle will make it out to those poles. So I can do Taylor series, I can sort of hook together Taylor series all over the place, and they'll all quit when they reach a pole, but when I put all those circles together, I can get all the rest of the plane. Yeah. Okay, so that's something about, I don't know how I got onto that department, but it's amazing. So the real and imaginary parts of that would be a flow, would give me a flow. I don't know if it'd be easy to compute it or not. Maybe I won't tackle that here. But yeah, we could find the real part of that and the imaginary part of that, and we would have a genuine flow field satisfying Laplace's equation with the two orthogonal, the streamlines orthogonal to the equipotentials. We could totally do that example, right? Okay, yeah, thanks.
So related to that, when you say one test question is based on the x plus I,
Yeah. Well, this sort of stuff, but the U would be the, yeah, that's right. Yeah, so when a test question would be something like, one way or another, you would end up with a U and an S, and the U plus IS, if they're a good pair, would be some function of this magic Z. Yeah, yeah, that's right. So whatever. We know examples, of course. For example, this could be x squared minus y squared, and the s that goes with that is 2xy, and the function that's involved there, when I throw in the I, is simply a z squared. Okay, that would be an example where the real and imaginary parts of this give us the good U, its good friend S, and the picture of streamlines and equipotentials meeting at right angles. Just a beautiful picture, all coming out of this function. So probably the quiz will have some other function. Yeah, yeah. But you'll still have a U and an S and a function of x plus iy. So if it's not this one, which I don't think it is, it won't be this one. This, because first of all, I wouldn't have mentioned it if it was, and secondly, that's a little too messy, I think, to get a good handle of to take the real imaginary parts of that. It's not impossible, of course. We could completely do it. There'd be some ratio of two polynomials. Here we have just simple polynomials, right? Okay, does that help with that question? Yeah. What else is on your mind? Any thoughts? Yeah, thanks. Curl. Okay, well, so I didn't really do 3 dimensions. So, but the curl is important. But we did see in 2 dimensions the key fact that all this stuff. Let me just write down what the great connections are between these, because I can't let the whole semester go without writing down that. What is it? Is it the curl of a gradient? The curl of any gradient of u is always 0, whatever it is, whatever u is. And this comes from, let me put the other one down, and then I'll just say why. The other one is like the transpose of this one. So if I transpose, so this is the 0 operator. Curl times gradient gives the 0. So if I just transpose, I still have 0. So if I transpose gradient, I have minus divergence. And actually, if I transpose curl, I get curl again. Of any, now I should put in, what should the curl act on? It acts on a W, I guess. No, I like divergence W. It acts on an S. Sorry. Yeah. Okay. And the minus sign, of course, isn't going to matter because I've got a 0 on the right-hand side. So S. Yeah. So if I take any field, yeah, I mean, this is like real proper vector calculus. To check these are, I call them identities, and maybe sometimes people indicate an identity, meaning it's always true for every u or for every s. They'll use the triple equal sign just to say they're really equal. Okay, so, and we could define the curl, but you've met it elsewhere, and maybe this isn't the time to do that. What's the key fact, the key little math business that makes all these true? So there's a sort of a formal math fact that makes them true, and then there's the physical understanding of gradients being, directions out with no rotation. So there's a physical understanding of that, but the math, the formal math fact is the fact that the second derivative of u with respect to x and y is equal to what? It's equal to second derivative with respect to y and x. Yeah, yeah. So you would find if you wrote out all the terms here or all the terms here, you would find that just by using that fact, they all cancel each other. Yeah, yeah. And the book, of course, does that. So we simply didn't do 3D in the vector calculus section. So I'll stop there with that, because it's really saying that the curl is tremendously important, and it measures vorticity in flow, and it's being able to, you know that, like, you take the Navier-Stokes equations. Well, the pressure and the velocity are the, what do you call, I mean, I'd say primary variables, or the natural quantities to measure pressure and velocity for a fluid flow. But you could also use these identities to set up in terms of other variables. Just rewrite the equation, and you get other things. This mentioning Navier-Stokes and fluid flow reminds me to say, we keep using the example of Laplace's equation. And a person could say, wait a minute, get beyond that, right? So why are you always, when you teach finite elements, why do you always start with Laplace's equation? Okay. Well, the main reason is it's the simplest one, right? It's the one where you can really see what's happening. More complicated equations would be for like elasticity, plane elasticity, or 3D elasticity, or other boundary value problems could be quite messy. But Laplace's equation is not totally a waste of time. First, it comes up when you have these scalar unknowns, and then it also comes up in numerical methods for Navier-Stokes. So the standard numerical method for Navier-Stokes, which would come in 18.086, ends up with Laplace's equation for the pressure. So to have a fast Laplace solver, as in today's lecture, pays off. Yeah, yeah. So I'm just saying, Laplace's equation is important in itself. It has the great advantage of being the simplest example we could possibly think of. It's the example where an x plus iy trick works. And it actually comes up in serious big computations because the equation for the pressure comes out to be a Laplace or Poisson equation. Now, I kept going there. Yeah, thank you.
So earlier this year we did a problem involving convection and diffusion.
We did, as a MATLAB problem, that convection. Sorry?
Where we had a second order and a first order.
And a first order, right.
Would you be able to derive a weak form of that?
Huh.
I mean, not right now.
Yeah.
Necessarily, but is that
I would do it the same way, but it wouldn't be symmetric, of course. That was the point about that convection term, is the diffusion term would be just what we've done, right? The diffusion term was that second derivative. And what would it look like in, as long as, we're close to it, what would convection diffusion in 2D look like? Just, part of your interest is pass 18.085 and get rid of it, right? But another part is, like, these are problems that, if you're in course 16, course 2, others, you're going to meet this. So what the diffusion part is going to be, again, in 2D, I'll have some minus u. Well, I made it simple because I took c of x to be 1. It could have a c of x in there. And what would the convection term look like? I'd have a velocity in the x direction, say a vx, and a velocity in the y direction, vy. Vy times, that's just a number. In the simplest case, that would be my river is traveling, or my flow is traveling along, and equals 0.
They don't have the same sign?
Sorry?
They don't have the same
I don't know which way the river's traveling, actually. Those are just constants. They could have positive or negative sign. The Vx and Vy is the constant flow that's carrying. What am I doing here? The flow is flowing along, and if those are constants, it's just flowing steady flow, but it's diffusing at the same time. And this would bring in that same difficulties that we met in the MATLAB 1D. So the MATLAB 1D problem just didn't have a y. I don't care, the sign I'm not worried about. It's just, is that there? Now I'm in 2D. And what would I expect to see? I'd expect to see some trouble when V is large. When V is large, convection, this is convection down here. This is the convection part. And if V is large, then so that this should be a lower order term is really fighting against this higher order term, I expect numerical difficulties, just the way we met. So anyway, if I did a MATLAB example, stretched it to 2D, we'd see a whole lot of interesting stuff. Yeah. We'd see flow in, flow out. Yeah. But I just can't do everything. But that would have a weak form. But your question about weak forms, weak form when you have this anti-symmetric term, for odd number of derivatives, is not quite as beautiful. But you have to deal with it, of course. Yeah, yeah. Okay, ready for whatever. Any thoughts? Let's see. You just have a look again at the list of problem topics to see if anything occurs to you. I mean, not that it should. You know, we're okay. I'm happy to call it a day on that, and time for dinner for everybody, and see you at 7:30.